Exercise 225 says, for each of the compounds below, locate the pattern, lone pair next to a pi bond, and draw the appropriate resonance structure. And so we worked through A through C in a previous video, so now let's go on and do some of the others. So first D. The first step here is to draw any lone pairs in a molecule. That'll help you to see if you have a resonance structure or a resonance pattern or not. So here, carbon is only going to have a lone pair if it has a negative charge. None of the carbons here have a negative charge. For the other atoms, the atoms that are different from carbon, which are called heteroatoms, atoms like oxygen or nitrogen, we just need to make sure that there are 8 electrons around them. Now, just so that it's a little easier to see, let me expand those bonds that are being expressed there. So the rest of the molecule, I'm just going to copy. We have that there. You have the nitrogen. And notice when it says NH2, that really means that this nitrogen has single bonds to 2 hydrogens. So that's really the same thing there. So this nitrogen, as you can see, has 2, 4, 6 electrons around it. And it needs a total of 8. So we'll add 2 on there. 8 electrons. Okay, so that is those are the lone pairs. And so now we want to see if we have any resonance patterns. We've only learned one so far. That's the allylic lone pair. First, we have a lone pair. Is it allylic? Well, notice you have to go one atom over. So here you have to go over just one atom to get to an atom in a double bond. And so that is the definition of being allylic. It's one atom away from an atom in a double bond. So we do have an allylic lone pair, which means we have resonance. Well, we've got to warn the world. This structure is not a true structure. It's just going to be one of several structures that we need to average. And so that's what those brackets are blaring out. Then we want to put that nice resonance arrow in, single line with 2 heads that says take the average of the 2 structures on either side. So when you learn these patterns, you don't just want to memorize allylic lone pair. You also want to know the pattern of curved arrows that go with that. So if you have an allylic lone pair, the allylic lone pair always goes to form a bond toward the double bond. And the electrons in the double bond always go to form a lone pair on the atom in the double bond that's further away from the lone pair. All right, so to draw the structure expressed by those curved arrows, we just copy the structure we have. It's the first step, exactly as it is. And then let's just zoom in on the hydrogens. We'll want to draw those in, any hydrogens that are involved on atoms that the curved arrows are pointed towards. So here, those are in the blue, those are the atoms that have electrons moving around them. When the electrons move, they bring their charge with them, and so the charges could be changing, the formal charges could be changing on any of those atoms. To calculate the formal charge later, that will be easier if we draw in the hydrogens on those atoms now. So first, this carbon right here. Now notice that carbon does not have a formal charge written in, and so it needs 4 bonds. And 1, 2, 3, 4 bonds are drawn there. So that carbon doesn't have any hydrogens. Next, this carbon here. It has 1, 2, 3 bonds drawn. That means there is an invisible 4th one to just 1 hydrogen. And you know it has to have 4 bonds because it doesn't have a formal charge. All right, so those are the hydrogens. Now that we have the hydrogens taken into account, we'll look at the curved arrows. So the tail of the curved arrow starts, wherever the tail of the curved arrow is, the electrons there are moving away from that place. And so we are going to erase those. And wherever the head of a curved arrow is pointing, that's where the electrons are going. So we'll want to draw electrons in. If the head of the curved arrow points at a bond, then you draw the electrons as another bond. Wherever the tail of the curved arrow is at, those electrons are moving. That's what the curved arrow is showing, the movement of those electrons, and so they're going to move away from that place, and you'll erase them. wherever the head of the curved arrow is pointing to, that's where the electrons are going. If the head of the curved arrow is pointing at an atom, like it is here, then you'll draw the electrons as a lone pair. Okay, now let's go back, figure out the formal charge on all of these things. Each of the atoms that the electrons moved around. So first, the nitrogen. Nitrogen is in group 5A, 5 minus, there are 0 dots around the nitrogen, and there are 4 lines around the nitrogen, so it has a +1 charge. How about this carbon? Carbon's in group 4A, 4 minus 0 dots around the carbon, 4 lines around the carbon, so that carbon has a 0 formal charge, 4 minus 4. This carbon right here, carbon's in group 4A minus, we have 2 dots around that atom and 3 lines, right? 1, 2, 3. 3 lines. And so that's 4 minus 5. That carbon has a negative charge. So those are your 2 resonance structures. And the true structure would be the average of those 2. So in the true structure, this isn't a double bond or a single bond, it's something in between. This isn't a single bond or a double bond, it's something in between. The nitrogen doesn't have a 0 charge or a full positive charge, it has something in between. And this carbon doesn't have a 0 charge or a full negative charge, but it has something in between. All right. So let's go through that same process for E. Now, the first step is to draw in all the lone pairs. A carbon will only have a lone pair if it has a negative charge. None of the carbons in this molecule has a negative charge. For the other elements, the atoms that are different from carbon, so the hetero atoms, hetero being a prefix meaning different, those we just want to draw the lone pairs in so that they have 8 electrons around them. So this oxygen on the left has 2 4 electrons already. That means we need 6, 8, 2 lone pairs around it. This nitrogen has 2, 4, 6, 8 electrons around it, so that's good. No lone pairs on that. This oxygen in the top right, that has just 2 electrons around it, so we need 4, 6, 8, 3 lone pairs on that one. Let me just put that a little neater. There we go. All right, so now that we have the lone pairs drawn in, we can look for resonance patterns. And the only pattern we know so far are allylic lone pairs. Those are lone pairs that are 1 atom away from an atom in a double bond. These lone pairs here are not allylic. They're not 1 atom away from a double bond, they're on an atom in a double bond. These lone pairs on this oxygen are allylic because you'd have to go 1 atom over in order to be on an atom in a double bond. So those lone pairs are allylic. So we do have that first resonance pattern. So we have resonance, we want to warn everybody, this is not a true molecule. The true molecule is the average of all the stuff inside the brackets. And we'll tell them to take the average with that resonance arrow that has only 1 line and 2 heads. Okay, when you learn these patterns, you don't just want to memorize allylic lone pair, because then you'll know there's resonance, but you won't know what to do. You also want to remember the pattern of curved arrows that goes with that. The allylic lone pair always goes toward the bond that connects the lone pair to the double bond. And the pi bond in the double bond, those electrons always go onto the atom in the double bond that's furthest away from the allylic lone pair. So to draw the resonance structure you get from that, copy the molecule just as it is. Just without the curved arrows. And we'll look at the atoms that the electrons are moving around. Those are the atoms whose formal charge could change, because the electrons are moving, and when they move, they take their charge with them. So if there are carbons there, we want to draw the hydrogens on them so that we can find the formal charges, the correct formal charges, a little bit easier later on. There are no carbons in that area, so we don't have to worry about drawing the hydrogens. All right, now we can think about those curved arrows. Anywhere where there's a tail of a curved arrow, those electrons are moving, so you want to erase them. Anywhere where you have the head of a curved arrow pointing, electrons are arriving there, so you want to draw electrons. If the head of the curved arrow is pointing at a bond, then you draw a bond. Any place where you have the tail of a curved arrow, electrons are moving away from there, and so you erase those electrons. Any place where you have the head of a curved arrow pointing, that's where electrons are arriving, so you draw the electrons there. If the curved arrow is pointing to an atom, then you draw the electrons as a lone pair. So now that we've moved the electrons, we'll go back and check the formal charges. So this oxygen on the left, oxygen is in group 6A minus, that oxygen has 6 dots around it and 1 line. That's 6 minus 7, so that oxygen has a -1 charge. This nitrogen here nitrogen's in group 5A, minus we have 0 dots and 4 lines around that nitrogen. So it has a +1 charge. So that positive charge there can stay. Next, this oxygen here, in group 6A minus, that oxygen has 4 dots now and 2 lines, 6 minus 6, that oxygen has a 0 charge. And so, the true structure of this molecule is neither of these structures. The molecule never looks like this and never looks like that. It always looks like the average of the two. So, I suppose if you were going to try to draw it, the true molecule would look a little bit something like this, with slight negative charges on the oxygens and a slight positive charge on the nitrogen. The average of those two structures. And the dotted lines here, the dotted line I have there is representing that the bonds here are something in between double and single. Single and double. Okay. Next. F. So for F, they give you this structure. First step is to draw the lone pairs in. Having the lone pairs there will help you to see resonance patterns a little better. So for carbon, carbon would only have a lone pair if there's a negative charge. And for any of the heteroatoms, those are atoms different from carbon, so nitrogen or oxygen, you just need to make sure that they have 8 electrons around them. So this oxygen has 2 electrons already, so we need to add 4, 6, 8. So that oxygen has 3 lone pairs. All right, so we have lone pairs. Are they allylic lone pairs? And they are. All of those lone pairs are allylic lone pairs because they are 1 atom away. You have to go 1 atom over in order to get to an atom in a double bond. Which means that we do have resonance, and we want to warn the world. We warn the world with these big fat brackets that tell them the true structure is neither of these, it's the average of the two. And we draw that special resonance arrow that tells you take the average of the things on either side. All right, you don't just want to remember the pattern, you also want to remember the curved arrows that go with it. And so the curved arrows that go with allylic lone pairs is the allylic lone pair always goes toward the double bond. It goes to make a bond, another bond, in the direction toward the double bond, and the pi electrons in the double bond go onto the atom in the double bond that's further from the allylic lone pair. So we'll redraw that molecule exactly as it is. And now let's notice that only these atoms here might have their formal charges change, because those are the only atoms that the electrons are moving around. So in order to calculate the formal charges for those later, we'll want to fill in any hydrogens that are not explicitly drawn. Hydrogens are always explicitly drawn on heteroatoms, so like oxygen or nitrogen, so if there's no hydrogen there, you would never draw that in. For the carbon, this carbon doesn't have a formal charge, so it needs 4 bonds total, and it has 1, 2, 3, 4 bonds already, so it doesn't have any invisible hydrogens. This carbon here has 1, 2, 3 bonds. It needs 4 because it doesn't have a formal charge, so there's 1 implied and invisible hydrogen there. Now that we've taken into account the hydrogens, we can move the electrons and look at the curved arrows. Wherever there's a tail of a curved arrow, those electrons are moving from that place, and so we'll erase those. Wherever there's the head of a curved arrow, electrons are going to or arriving at that place, so we're going to draw electrons there. If the head of the curved arrow is pointing at a bond, then you draw in another bond. Anywhere where you have the tail of a curved arrow, electrons there are moving, and so you erase those electrons. Any place where the head of a curved arrow is pointing, electrons are arriving there, and so you want to draw electrons. If the head of the curved arrow is pointing at an atom, you draw the electrons as a lone pair. So we've moved the electrons. Now we have to think about how that changed the formal charges. So let's start with this oxygen up here. Oxygen's in the group 6A. There are 4 dots around the oxygen and 2 lines around it. 6 minus 6 is 0. That oxygen now has a 0 charge. This carbon here, carbon's in group 4A, 4 minus 0 dots around that, 4 lines, 4 minus 4 is 0. That carbon has a 0 formal charge. Lastly, this carbon here, carbon's in group 4A, minus 2 dots and 3 lines, 1, 2, and 3, the line to the hydrogen. So that's 4 minus 5. This carbon has a negative charge. So the true structure is not this structure on the left. It's not this structure on the right. It's something in between. It's the average between the two. And so I guess if you were to try to draw it in a sort of vague way, it would look a little bit like this. So that these bonds here are neither single or double, there's something in between, and the charges are not full charges, because in one resonance structure they're full and in the other they're 0, so they're only partial charges in the true molecule. Alright. Let's do this with acetylcholine. And actually, I'll do this in a separate video, just to avoid making the videos too long.